And welcome again to our second module. And the theme here that we are discussing is machine learning and artificial intelligence and its applications in the field of OBGYN. We've had a really interesting session before in module 1, and I look forward to this session. We have an expert panel lined up for you, who I will introduce in a minute. A little bit of my background. My name is Dr. Naila Siddiqui Kamal. I'm often known as the geeky gynecologist as I blog in AI Med. And my area of interest is always disruptive technologies and what they can do for delivery of healthcare in today's age, and especially in our area, that is ops and gynae, where there is a lot that can be achieved due to challenges that we see, especially in the face of this COVID-19 pandemic. So without much ado, I'd like to introduce our first panelist for this session. And what we are going to do is that I'll introduce both of them one after the other, and because they would be doing a joint presentation, one following the other. And then after that, we will take questions. And I've got some questions lined up because this is my area of interest. And I'm sure you will enjoy and really appreciate what advances that are happening in our specialty. So first panelist is Dr. John Havelock. He's a reproductive endocrinologist and infertility specialist at the Pacific Center for Reproductive Medicine. Dr. Havelock's area of focus is infertility, recurrent miscarriages, polycystic ovarian syndrome, infertility surgery, and reproductive endocrine disorders. I'm sure that we will look forward to how artificial intelligence and advances in technology are impacting these very crucial areas of our specialty. I'm going to ask Dr. Havelock further to expand on his accolades, which are in front of his name, because he can do much more justice with them. The second panelist following John is going to be Parveen Saidi, who is a PhD, a doctorate, and she's done an MSc and PhD in electrical and computer engineering from the University of British Columbia. She's currently the Associate Dean for Research and Graduate Studies at the Faculty of Applied Sciences at Simon Fraser University. Again, I will ask Parveen to further expand on her connections and expertise so that our listeners can get the full appreciation of what your backgrounds are. So I'm going to pass over the fort to both our panelists, whoever is going to go first, whether it's Parveen or John. John.
It'll be myself. Thank you.
All right, over to you guys.
Thank you for the introduction. So my name is John Havelock. I'm a reproductive endocrinologist and fertility specialist in Canada. I'm a co-director at the Pacific Center for Reproductive Medicine. We're a 3-center IVF clinic in Western Canada. My training in obstetrics and gynecology was done in Canada, and my reproductive endocrinology and fertility training was done in Dallas, Texas, United States. What we're going to be talking about today is the automated assessment of embryo morphology towards improvements in embryo selection. I'm going to start by talking about the background, the rationale for this research, and discuss my collaboration with Dr. Parveen Saidi, who's really done all the difficult math and groundbreaking work in this area of research for us, for which I've been a collaborator. An individual has come up with some of the ideas, but the real difficult math and AI work is being done by Dr. Saidi, and she will discuss that after I discuss the rationale for this work. So why do we need embryo selection technology? So the goal in vitro fertilization is to affect the birth of a live, healthy term delivery, and we want to maximize the chance of pregnancy and implantation while minimizing risks, one of the great risks being multiple pregnancy. In order to do this, we need to limit the number of embryos that we transfer into a woman's uterus. And in order to make this the most efficient treatment possible, we need to have an ability to determine what are the best embryos to transfer and which ones aren't. So we need some tool for selecting the best embryo to transfer. And we do know from the beginning of IVF, first birth in the UK in 1978, that some embryos have better implantation potential than others. Now, if we look at a population, assume every embryo has the same ability to implant, and we assume the implantation potential is around 30%. If we have no ways of stratifying which one's better than the other, we may be spending a lot of time transferring embryos that really don't have any ability to achieve a pregnancy. Now, the perfect tool would allow the binary determination of implantation potential. So if we take these 10 embryos where we have no ability to select, and we have a tool that can allow us to determine which embryos absolutely have no possibility of implanting and which ones we know for sure will implant, this is the best tool and the most efficient way to perform embryo transfers if we have an embryo selection technology tool such as this. And there are some tools that are better than morphology, which we're going to concentrate on discussing today, such as pre-implantation genetic testing for aneuploidy screening, where a few cells are taken off a day 5 or day 6 embryo, and those cells are tested to see if the embryo is aneuploid or euploid. And we know through some of the randomized controlled trials and validation trials in this that if we have an embryo that's determined to be aneuploid, that essentially has close to a 0% chance of resulting in a normal delivery. These types of tools aid us in determining better which embryos are better than others. Problem with that technology is that while it allows us to identify the embryos that aren't going to implant, so it has very good negative predictive value, its positive predictive value is definitely not 100%, and there's some emerging evidence to suggest when you biopsy these embryos, it may actually affect the ability of that embryo to implant. So it may be damaging to the embryo. It's also costly and time-consuming to our laboratory technologists. So it's not a perfect tool. And still, throughout the world, the tool that we use most is embryo morphology, and it's the most common way that we assess embryos. And essentially, we develop a ranking, a scoring system for these embryos based on morphology. But again, an embryo is not going to have a 10% or 30% or 50% chance of resulting in a baby. It's either going to result in a baby or not result in a baby. So it's not a perfect tool. And what do we do for embryology assessment? So data is being published in the reproductive endocrinology and fertility literature as early as the early mid-1980s by Steptoe and Edwards, who developed and pioneered the first IVF birth, looked at how quickly embryos develop and cleave, and the descriptions throughout the literature have advanced until today. And what we typically look at is at least on the day 3 embryo morphology assessment, which was in the past the most common day for an embryo transfer. The most common morphologic characteristics we were looking at were cell number. So you can see in the 2 boxes on the left-hand side of the screen, where you can easily on day 3 count the number of cells. This one at the top looks like 4 cells. The one at the bottom, 7 or 8, and this really involves sort of a dynamic look at the embryo, scanning up and down through serial planes to do cell counts, and you can get a pretty accurate assessment of count. Middle is looking at fragmentation. You can see at the top middle image that there's very little fragmentation, and the bottom one, this significant degree of fragmentation. This is not a good prognostic finding. You have a hard time seeing the cells, and a lot of those cells that seem to have really fragmented into a bunch of cellular debris. And again, this is a poor prognostic factor. And then on the right, we see cell size. In the top right-hand square, you see a 4-cell embryo. The cell size look pretty much the same, whereas in the bottom right-hand size, you can see some asymmetry between the cells. And the more symmetrical the cells, it seems, from retrospective assessments, that this predicts implantation. So the problems with morphology assessment is there was very little standardization between facilities and between countries. at least in North America, the Society for Assisted Reproductive Technologies in 2006 developed a standardized staging and grading system for these embryos on day 3. And so grading would be either graded good, fair, or poor, and that's a somewhat subjective assessment system. And then there was staging, which is a semi-quantitative assessment of fragmentation and symmetry. So good would be 10% or less fragmentation and perfect symmetry. Fair would be 11 to 25% with moderate asymmetry, and poor would be more than 25% fragmentation or severe asymmetry. And again, semi-quantitative, but still very subjective. And we'll talk about the inter-observer variability in a moment. Data was published in 2014 looking at day 3 morphologic assessment and using good as the grading reference population. You can see fair embryos implanted and result in live birth at a similar rate as good embryos. Poor embryos, so about half the rate of live birth. If we look at cell number, 8 cells on day 3 is the best number of cells. And if the embryo is cleaving too slow or even too fast, it seems that the embryo is less likely to implant. And then if we look at fragmentation with no fragmentation being the reference range, you can see with increasing levels of fragmentation, the embryos are less likely to result in live birth. So this scoring system did result in a standardization and also did predict outcomes. There are some problems. There is a fair bit of inter and inter-observer variability. So this is a study looking at 5 embryologists analyzing 90 embryos at 2 different time points to get the kappa coefficients for inter and inter-observer variability. 0 to 0.2 for your kappa coefficient is poor, 0.2 to 0.4, fair, 0.4 to 0.6, moderate, 0.6 to 0.8 is good, 0.8 and above, excellent. And you can see in cell number, day 3, where it should be pretty easy to count between 1 to 8 cells, you got a good but not excellent inter and inter-observer variability. Fragmentation was not quite as good. It was in more the moderate correlation. Size of blastomeres, again, inter and inter-observer variabilities. With inter-observer, it was even in the fair range. And decision. So decision meant, were we going to transfer the embryo? Were we going to freeze the embryo? Were we going to discard the embryo? In spite of differences in scoring for the cell number fragmentation blastomere, there was quite a good correlation between decisions. So embryologists were more common to make the same decision, but it wasn't excellent and it wasn't perfect. So we did see that there was a fair bit of significant inter and inter-observer variability. More importantly, there's been a shift towards transferring embryos not on day 3 but day 5, and which are called blastocysts. And so we've got a greater concentration on looking at blastocyst morphology, where now almost 2/3 of the embryos that are transferred at the blastocyst stage. These are more complex structures. You can't count cells, so 200 to 300 cells, so you're not counting the cells. There are certain morphologic characteristics of the embryo. So on the top row of the 3 embryos, going from left to right, you can see embryos that are increasing in expansion. So it's small on the left, a little bit more expanded in the middle, and fully expanded on the right. And in the bottom, these are hatching, the bottom left, and hatch. So there's a little ring that is very difficult to see, which is the zona pellucida. And once the embryo breaks through the zona pellucida, that's called a hatching embryo. And when it's completely out, is hatched. You can see, if we concentrate on the top right image, you can see this sort of round little structure bulging at around the 10 o'clock position. This is the inner cell mass of the embryo. The fate of the inner cell mass is to become the future fetus and child. And the ring of tissue that forms around that is the trophectoderm, which its fate is to develop the placenta. And if you're doing pre-implantation genetic testing and biopsying the embryo, you avoid the inner cell mass and you take a few cells from the trophectoderm. But as I had said before, this may be somewhat harmful to the embryo. And when you do it to an embryo that's actually a euploid embryo, you might be impairing its ability to implant. So we really are trying to concentrate on non-invasive means to assess embryo quality. Again, in North America and in Europe, they have developed scoring systems and have tried to standardize things. So they look at the stage of development, how expanded it is, how big the embryo is. They look at the inner cell mass and grade it good, fair, or poor, 1, 2, or 3, and then the trophectoderm, 1, 2, or 3. And this really is scored based on more cells tightly packed together are good, and the poor ones that are very few cells are really the poor embryos. In the middle is in between there, which is classified as fair. But one
John,
person.
Sorry to interrupt, John. Would your presentation, is it okay if you go into Parveen's time, because it is now
pretty quick? Yeah, I'll finish up fairly quickly.
Okay,
here. Yeah,
all
thanks
right.
for so if we looked at this, we can see that the good embryos were more likely to implant than the fair or poor. Expanded and hatched blastocysts, so more expanded, were more likely to result in live birth. And when the trophectoderm looked good, it was more likely to result in a birth. However, again, when we did the intra-observer variability, we can see that actually the inter-observer variability is even worse on the blastocysts than on the day 3 embryos. And while the embryologists, when they looked at this, had good correlation to decide which embryo they were going to transfer, only half the time would they pick the same embryo for transfer. So again, there's still a fair significant inter and inter-observed variability, but good variability in embryo selection. We need some better way to standardize things, and automation may provide a means for that. So what are the potential applications for this? Eliminating that inter and inter-observed variability, improving quality control measures for embryo selection for transfer, reduce the need for training and embryo assessment, which is very time consuming and costly, and allows for greater accuracy in assessing additional parameters. So my apologies for going over time. That's a background for why we do this. I'm going to leave Dr. Saidi to explain how we've been doing this, and thank you for your time.
Thank you, John. Hi, everybody. My name is Parveen Saidi. I'm an associate professor at Simon Fraser University in Faculty of Applied Sciences. Thank you for having us. I would like to start my presentation. Let me just share my screen. My background is related to machine vision, which is a field that allows us to capture, process, and analyze and understand the content of one or more digital images that are taken from any environment with any subject within it. Our objective is to create numerical or symbolic information that can help us to understand what is going on in that environment. Some of the examples that everybody might have seen and never known that there are machine vision technology in them are around us. For example, in medical field that I'm sure many of us have experienced, in surveillance, all the police cars that are going around, they don't need to type anything. They can just get all your information through your car. Even iRobot or vacuum cleaners that are going around, they do have a machine vision in them that create a map of your environment. And more, in fun applications, all the gamings, or in industrial built and inspection or for security purposes, all of them have a machine vision element in them. What a digital image is nothing but a matrix of numbers. And in these numbers, you have a coordinate and a value. The value at each point represents the intensity, that is a value from 0 to 255. And usually for a grayscale image, 0 is black and 255 is white. And anything in between represents a range of grayscale. If you have a color or composite color, what you have is 3 matrices, and each one of them corresponds to one of the elements of red, green, or blue, and together they will create that composite color for that specific pixel. So what we work with is basically these numbers and their neighborhood in that aspect. As John mentioned, our objective in this project is to create a machine vision and artificial intelligence-based systems that can give us a complete guidance in selecting embryos with the best implantation potentials, leading to that one healthy baby at the end. And what we would like to do is to look at the kinetics of the development, as well as the morphology and visual characteristics of these embryos during the time that they are in the incubator, which is about 5 days at different times. We would like to look at them and then be able to assess them. A system of such will allow us to create quality assurance measures that helps in creating new standards for selecting all these good embryos, and then placing our fertility experts on the leading edge of this treatment. Initially, we started working with PCRM back in 2012, as I was a patient myself that I've got two beautiful babies with the help of Dr. Havlock and his team. So my heart is set in this field. It's more than just a research for me. At the time, there were only 5 published papers as we could find. So it was very, very new. And these works weren't even automatic. They were semi-automatic mostly. Out there. And because the new embryoscopes that provide time-lapse images are fairly new, everything was based on single images that were taken daily. They were taken daily from each embryo at one specific time. So it was like single image processing that we were doing. And our objective initially was to create handcrafted algorithms that would create this specific feature for this work. And we used mathematical models that could explain texture or some sort of visual attributes of these components that we were trying to identify, and then go from there. You can see that developing such algorithm is very custom, and it varies from one application to another. So it was very specific to this research. The very first work we did was to identify the thickness of the zona pellucida, as Dr. Havlock mentioned. The thickness is a very good indicator of whether the embryo will be implanting or not. And because also the shape of an embryo is an oval, we had a very good description of an ellipsoidal model for in terms of the mathematical equation. So we were able to go with that and create these models. Our initial accuracy at that time was about 75%, mainly because the models that we were creating wouldn't fit to the local boundaries of these zona pellucida, but rather to the entire zona pellucida. So we wouldn't do that. So that wasn't bad. And what we noticed is that as the embryo gets better and the thickness of the zona pellucida becomes smaller, even 1 pixel error would contribute to a larger amount of error. So we realized, fitting a model might not be the best, and we have to go a little bit more local. The next thing we did was we wanted to identify the regions associated with ICM, the inner cell mass, and trophectoderm. And for that, what we did a little bit of studying the structure behind the visual image that you can see in here in the middle, and the one that is right next to it in your right side. And we created these mathematical models like entropy, which shows the randomness of a pixel in comparison to its neighborhood, contrast, standard deviation, homogeneity, energy, that each one of them would represent a measure. And a combination of all these measures together, we characterize the different regions for TE and for trophectoderm. As you can see in the image in the middle, the zona pellucida's outer boundary is very faint. Really finding that boundary is not an easy task using the models that we have. So for that work, the second part that we were finding the areas associated with T and ICM, we were able to deliver relatively good results. The first row shows the results of our work for trophectoderm, and for each case you can see the bad, average, and good. And for the ground truth is the second row, and the difference is shown in the last row. And similarly, we have that for our ICM. And you can see that in many cases we do very well, but in some cases we don't do as well, mainly because it's not as easy to separate TE and ICM. After all, they cell-wise, they look very, very similar. In terms of the results that we were getting, it's interesting to see that our accuracy for identifying trophectoderm region was 86% in average for different grades. And for ICM, we had about 90% accuracy. However, what we don't like in image processing is just to look at accuracy, because to us this is not a very good representation of the whole process. What we like to use is Jacquard index, and Jacquard index penalizes not only for your like rewards you not only for all the good ones that you have found, but also penalizes for all the ones that you are missing and all the ones that you falsely claimed as being the region. And the value is similar to accuracies between 0 to 100%, and in this case our Jacquard index was at 63% for TE and 65% for ICM. But since then, starting from 2015, we started moving towards machine learning and in particular, deep learning algorithms. What is interesting about these neural network-based systems is that you remove the task of programming, custom programming for a specific job, but rather you use architecture that can generalize solution for different applications. For these sort of methods, what you need is a set of training images, which is basically ground truth that is identified by the expert, and then you train your system with millions of parameters, and through those you can basically get any unknown input of the same type and then predict the output. Clearly, you need more training data in order to get more accurate. That's something given for this machine learning. And we're not talking about a little, we're talking about thousands and millions of samples. And that's probably the challenge that we have. The very first thing we did was to find the zona plucidas using this method. So we put the system together, but one attribute of this system was that it wouldn't be a global model, but rather a local. And that would be advantageous because it fit to the exact boundaries of a zona plucida. And even though it looks complicated, it wasn't that hard to put it together. The input was just the mask of the zona plucida for those that the human expert or the embryologist expert had identified, plus the input image. And what we got was this output that substantially improved in terms of the results. For our best case scenarios, we had between 95 to 100% in Jacquard index, which is not very little. It's very hard to get that final 10% of Jacquard index. And for average cases, we had between 85 to 90%, and for worst cases, we had 70 to 75%. The blue ones are the ground truth. This is the red one is our output, and we had some post-processing that help us to even improve our results better, that are shown for these different variations in the last three columns. So what we get at the end was an accuracy of 95% with a Jacquard index of 78.1%, comparing to what we had before for 59. And given that the number of samples were increased by at least 4 times, you can see that this was a very good improvement. Next thing we wanted to do is to find these regions associated with trophectoderm and zona plucida using deep learning. And this work was one of my PhD students who is graduated, and he was nominated for Best Student Award in the most prestigious image processing conference. This is the output of our system. The second column is the ground truth, and the last column is our work. In between are some of the very famous networks that are developed by big companies like Google and Microsoft, and we beat all of them. The reason for that is that we created a specific additions to these architectures that existed, and based on the dynamic of our data and attributes of our data, and that made the system different. And what we were able to achieve was for zona placida, we got a Jacquard index of 81.5%, TE 76.52, and for ICM 81.07. Again, you can see that from the handcrafted, comparing to those handcrafted methods, we have substantially improved. TE was 63, now we are at 76.5, and ICM was 65.8, and we are now at 81%. The last thing we did was to put all these things together and say, forget about these regions. We wanted to grade, but what if we use input image and see what we can predict in terms of the output? Can we predict the output in terms of the implantation? That's what we did. We basically created a system that as input used original images that we had plus the output of our previous system for these regions, 3 regions that we had calculated through machine learning, and feed it into our system. And what we would get in the output would be whether it's a positive pregnancy or negative pregnancy. Granted, each one of these input images, because they were from patients, we had the outcome for them. But these two, stream B and stream C, they were all done by our automatic system. So we really had very little training to do, very little expert embryologists to be involved to do that for us. And what we were able to do was pretty amazing. The expert embryologist, for all the samples that we had, which was about 500 samples, the accuracy of the outcome prediction, because when they put an embryo back, they think it's the best. They're hoping for positive. But 50.7% of the time, they only had a positive implantation. And that almost another 49.3% is negative. But with our technology that was sitting over the selection of the embryologist, we were able to improve the accuracy by 70.9%. So that's about 20% improvement in selecting the embryo if an embryologist gives us his best pick, and then we put our AI over the top of that and say, put this one, we have 20% higher chance of getting positive pregnancy results. And again, we haven't done it from scratch, so we rely on embryologists to give us some of their best, and then we say which one are the best. We can obviously, our next step is to try to see if we can remove the embryologist and see what our AI would do, but that requires more data, and that takes a little bit of time for us. Currently, what we have in terms of ongoing projects is that we wanted to be able to annotate our sequences, because now we have access to image sequences. We wanted to annotate because we believe that there are specific transitional times that people may not notice as much change, but the artificial intelligence might pick up some. So we wanted to be able to annotate the data automatically, as well as be able to use the entire sequence from day 0 to day 5 to select the best embryo for implantation. I'd like to thank Dr. Havlock and his team. They have been wonderful to work with, and our work wouldn't be possible without them, as well as my graduate students and NSERC, which is the National Science and Engineering Research Council of Canada, for funding us. Thank you so much for listening. And I will be very happy to answer questions.
Thank you so much, Marine and John. That was really enlightening. And I've been following very closely the developments, especially in artificial or assisted reproduction, because often I get requested to talk about futuristic healthcare, in general, and especially in ops and gynae. And this is one of the areas where everyone is very keen to know what are the next steps. So question to you first, and then I'll go to John. What is the next step in AI-based applications for human embryology quality assessment? And I'll give you a backdrop of something which is interesting. I saw a a couple of weeks ago in the subfertility clinic, and the male partner had cancer, and he had his semen sort of frozen, and now they are seeking IVF. And the issue is that there isn't much of a sample there, and their concern is how best to ensure that they get a positive outcome. So while you were presenting about the quality of the embryo and all that, I was thinking about that patient, that how they would have benefited from this technology. So over to you.
Great. Yes, of course, yeah. The next step, I think, would be, in my opinion, to sit with, like, I think in order for these projects to be successful, and I know many researchers now are working on this area, is to be able to have more data. Not having enough data is a limit. And we are the very first, and I think only group, who have shared our data with the community, because me and John, both of us are very much believing in open sources to allow for the science people to use everything that is available for obvious reasons. So having a big infrastructure that would allow people, cloud infrastructures that would allow people to share their data and create this big data set of embryos at different conditions is a necessity. And unfortunately, that's something that hasn't happened. And I'm not sure why this is going on, but unless everybody comes together and share those data, it's not possible to make more big steps in this field for fertility. Also, I think the policies of the governments are more towards aging people than people who are dealing with fertility issues. That is 8% of women. And I wish that there would be more initiatives in terms of different places to support such research. But I think the next step pretty much is to be able to collaborate at different places and come together to make this happen, with the use of more data. That's what I think it would be.
Thanks so much, Praveen. And John, would you like to add something to that
Yeah,
question?
I would have to concur with Parvane. More data. It's when you look at some of the more recent publications in the clinical literature on this, they're looking at several thousand embryo transfers, and it's really tough in a short period of time to get that kind of data from one center. You really need multiple centers willing to collaborate and share that data. And I mean, I think there's a couple issues, health privacy and obviously getting approval through the research ethics boards. I think there's a bit of a proprietary concerns. As technology, definitely there's a push towards commercializing it, and as a result, it's tougher to get access into large data sets for the AI, for testing and training the AI technology, which Parvane could comment more on that than myself. Obviously, at some point in time, the goal is going to be to have it developed robustly enough that we can put this into a trial where we can compare human embryology assessment to the basically the AI, and seeing which is a better tool to selecting the embryo.
What comes to my mind, because it's been a long journey, when I sat in awe and listened to Robert Winston, who's the father of IVF in as far as this generation is concerned in the UK, when he spoke about assisted conception and the achievements, and we have come a long way from there. I can see the one thing that was also asked at that time is still persisting, which is sharing of data and the barriers that are there, and the governing systems of information that are surround this emerging technology. Unless there is a strong body that understands what this technology is about and is able to communicate it to all stakeholders in a very clear manner, because I think half the reason why people don't share data is because they're scared of the unknown unknowns. And that is why people don't agree to it. That is what I feel. But you've made a very important point. And I had some more questions here, and both of you, whoever wishes to answer them, that are there any other embryo assessment standards that this technology can be measured against? So
I mean, for me in the lab, I know what more commonly that there have been some studies trying to assess it against a euploidy or aneuploidy to see which embryos are chromosomally normal and which ones aren't. It doesn't, at least to the literature that's out there to date, doesn't seem to work very well. Obviously, hopefully that'll get better. It can seem to assess chaotic aneuploidy or complex aneuploidies where there's multiple chromosome abnormalities, but on a single trisomy or monosomy, it doesn't seem to work quite yet. The gold standard obviously is normal live birth. But it's really, euploid is the other surrogate marker we're looking at. And embryo kinetics, taking multiple images of the embryo and seeing how it develops over a period of time, or time-lapse morphology is the other area where there's more data. But again, at least using the human eye, whether or not that gives you more data that's helpful is really up for debate. But maybe AI is better than the human eye.
Yeah, and I must add that the recent work that we have, and we have submitted 4 papers now, are under review for this year. We have been combining day 3 plus day 5 on image sequences. And so we are getting full images for 2 days, and we have combined, and we got 6% improvement in the results. I haven't brought this in because we want to publish them first before talking. Yes.
I'll be looking forward and following your publications, and definitely watching out for the outcomes of your really impressive research that you guys are doing. So thank you so much for being the panelists here and allowing me to be the moderator in my humble way. I hope you've enjoyed being part of this panel, and I'm sure the listeners would have really enjoyed and be impressed by what they've heard.